Welcome to the CircuitPython show. I'm your host, Paul Cutler. This episode I'm joined by Joey Castillo. Joey is a hardware and software engineer based out of San Antonio, Texas. In 2019, Joey began branching out into hardware and electrical engineering. He created Oddly Specific Objects, a division dedicated to designing, manufacturing, and selling comprehensible open source gadgets for hobbyists and creative technologists. This episode is brought to you by PCBWay. With over a decade of experience, PCBWay is one of the most experienced manufacturers in PCB prototyping and design. Whether you're an engineer, student, or hobbyist, PCBWay offers a simple and fast prototyping service, and it's cost-effective at only $5 for 10 PCBs. And check out PCBWay.com/project, where PCBWay helps makers and hobbyists collaborate on their designs and projects. Make your design a reality and check out PCBWay.com for all your PCB needs. And they also now offer CNC machining and 3D printing services. Visit PCBWay.com for more information. Thanks to PCBWay for their sponsorship. Joey, welcome to the show.
Howdy, good to be here.
Tell me how you got started with computers and electronics.
So, I guess how I get started with computers and electronics, it starts way back. I mean, I was like into computers as a kid, like, I don't know, like my aunt gave me her compact portable from like the 1980s when I was in like grade school, and I started playing with that. Also tried soldering things together as a kid, but never really got very far. In more recent years, I got into software engineering, doing kind of iOS apps, App World, Appland kind of stuff. And that's from there, I started kind of hacking back again on electronics projects back in like 2019 or so, and kind of started to really make a go of it. And now I'm doing this oddly specific objects thing. So
tell me a little bit about Oddly Specific Objects.
I started in 2019 with the kind of the quixotic, I forget how to pronounce that word, dream of building an open source ebook reader. And at the time, like I didn't know enough to know how to build that. So I started off with some simple projects, and my first project, I called it the hiking log. It was a 3D printed log, and inside was a feather and a GPS wing and a temperature sensor. And I could throw it in my backpack when I go on hikes, and it would log my location and temperature data when I go camping. I thought to myself, like, it's a data logger that's shaped like a log. That is an oddly specific object, and that was where the name kind of came from. Since then, I've started, building more of these like kind of gadgets for sale. So I have the sensor watch, obviously, and then the LCD Featherwing. And yeah, oddly specific object just feels like it's kind of like the box into which I put those kinds of projects, more or less.
I wanted to ask you about the LCD Featherwing. You recently tweeted about implementing the I2C driver with CircuitPython first, before Arduino. Tell me more about the LCD Featherwing and what led you to that decision.
So the LCD Featherwing, it's a kind of a simple gadget. I mean, it's making it a little complex, but essentially, it's a raw LCD glass, which requires being driven by some kind of fancy analog signals, and a chip that translates between the I2C protocol that we all know and love and these kind of very analog kind of LCD driving signals. When you bring up a new thing, there's all kinds of things that can go wrong. It's like, did I wire it correctly? Did I like mix up my TX and RX lines? Did everything powered properly? Am I sending the right bytes over the bus to initialize it and display something on the screen? And when you're working kind of Arduino world, you can call begin on the I2C bus and you can send some bytes, but you're kind of just keeping your fingers crossed. Whereas with CircuitPython, if you forget to have a pull-up on your I2C line, you're going to get a message in the console telling you that you made that mistake. So when it came time to write the I2C driver, there were a couple of factors that led me to go CircuitPython first. First of all, it was just really easy to get started and make sure that I had it wired up correctly. I had one thing where I was like, why isn't this working? Well, there's no device at that address. Well, CircuitPython told me there's no device at that address, and I went back and checked my data sheet and put the correct address in. But that's the kind of thing that could have had me flummoxed in Arduino land for a while until I scanned the whole bus. But seeing a really simple error message telling me this is what's wrong meant that I could iterate quickly. And I guess that's the second thing, fast iteration cycles. If I was doing these character mappings where it's like which segment maps to which position in a byte. So if I have something wrong there, in an Arduino sketch, I go in and I edit my bit masks, and then I compile and I upload. Whereas with CircuitPython, if I change that bit mask and I just hit the save button, the code automatically restarts and I'm in business. That really super fast iteration cycle of working in CircuitPython really made it an obvious first choice for developing the driver. I want to support CircuitPython users, of course, but it's actually much easier for me as a builder of gadgets to get started there. And then when it came time to do the Arduino driver, I more or less just started with my Python code, copied it into a C++ file, and started just porting over line by line what I had done. But all of the hard part, all of the thinking part was already done by past Joey in Python. So that was kind of the thought process behind building the CircuitPython driver first and then the Arduino driver.
That's been a common theme on the show, is that fast iteration cycle and that immediate feedback you get from error messages.
Yeah, no, it's just really great. And again, it's the kind of thing that could have you flummox, because you start out with this thing of you have all of these possibilities that the issue could be, and the faster you can get narrowed down to what it might be to what it is, the sooner you can address that and find the next inevitable issue. And you knock over enough issues and then you're done.
You mentioned the OpenBook earlier, which is an open source e-reader using a Raspberry Pi Pico. How did you develop the user interface for an ebook reader?
I mentioned in the beginning, I kind of started in app world and iOS app world. And so in the beginning, I used UIKit, which is this really cool kind of event-driven system. And I still find it really intuitive. If you have a window, okay, so you have a window, and then into that window you add a table, and in that table you have a bunch of cells, right? If you wanted to lay something like that out, you wouldn't want to work in raw screen coordinates for that, right? So you have the window, and you add the table as a subview of the window, and you add the cells as a subview of the table, and you have the label as a subview of the cells, and everything kind of just lays out recursively, and it just works. So when I wanted to do the OpenBook, I really wanted to have a user interface framework like that would let me kind of lay things out in an intuitive way. And this was another thing where I actually got started with that in CircuitPython, because eventually when I wrote this in C or C++, most of my time was spent wrestling with pointers and smart pointers and weak pointers and shared pointers. Whereas in CircuitPython, I can just define my objects and define the way I want my objects to relate to other objects. And in this case, I kind of piggybacked off of display I/O, because my views in my user interface hierarchy are actually just groups with some extra stuff sprinkled on. So once I started to do that, it was very easy to okay, now my layout is working recursively. Now I want to have a tap, and I want to see where that tap hit. So I can start with a screen coordinate and recursively work my way backwards to figure out which object on the screen received that tap. And then that kind of bubbles up throughout the view hierarchy to the point where okay, my cell can have a chance to respond to that tap, and then my table can have a chance to respond to that tap, and then my window can have a chance to respond to that tap. That's a really kind of a complex system to kind of build out from scratch. But starting in Python world, it was fun. It was actually really quite easy to iterate quickly on that. Not only that, but once the framework was kind of built, I was able to easily use some of the CircuitPython libraries that existed to build cool stuff on top of it. Whether it was taking just sort of the Adafruit has the little CircuitPython characters, the little resistor named Mo and all that, the little characters. Making a little table with those characters and using a D-pad to navigate between them and tapping on one and popping up an alert. That was just a very simple way to demo something out, using just the Adafruit display shapes library and the Adafruit image loader. But then I think it was Jeff Epler did a MP3 player in CircuitPython. And so I was cool, I'll take the MP3 player and I'll port it over to CircuitPyUI, which is the name I had for this UI framework. And in an afternoon, I was able to put together a working MP3 player using the buttons and sliders and progress bars that I built in CircuitPyUI. So it ends up just the kind of the really fast iteration cycle. I was able to build cool stuff that I actually like playing with, but also it kind of exposed some of the cracks or challenging areas or the rough edges I needed to sand off of CircuitPyUI, and that ended up giving me a very robust kind of event-driven, recursively laid out kind of UI system. At one time, I actually did think I was going to build the entire OpenBook UI in CircuitPython for a couple of reasons that didn't work out exactly as I hoped. But when it came time to build the whole thing in C++, once again, just kind of my I2C driver, I've got this really well thought out framework that I've built in Python, and I've done it in this high level language that takes care of a lot of that stuff for me. Oh, my view's gone out of scope. It's garbage collected at some point and it goes away. Now it's up to me a little bit to manage that scope and to figure out whether a pointer's weak or who has to hold on to what. But the hard part of how should it work, that's all something I got to think through in a high level language like Python, which is it's a huge asset.
What's next for the OpenBook?
So what's next for the OpenBook is I've got this Raspberry Pi Pico-driven version of the OpenBook, which is really finally easy to hand assemble. Like, this has been my main thing. The OpenBook has always been, the vision was a do-it-yourself ebook reader that someone can build from scratch and understand. And now I've got it down to a small number of parts, all relatively large. I'm going to bring 20 of the OpenBook kits to SuperCon in California to hopefully get to people out there. And I've also published all of the design files so folks can order the parts and build it themselves. If they want to get 20 of them and make it a project at their hackerspace, they could do that. If they wanted to get 100 of them and sell the kits in a country where I can't sell things easily, like, have at, like, steal this book. That's kind of phase one. And I'm kind of calling this version the, like, developer preview edition because it's kind of got chunky AA or AAA batteries sticking out the back. So it's not as svelte as a lithium polymer battery oriented solution might be, but that also means the part count is lower and it's easier to deal with shipping and transportation and all that. So yeah, what's next for the OpenBook is the kind of developer edition, and then we'll see. Next year I'm going to clear my plate off of a lot of things, and then we'll see what I can build.
Well, that's great to hear. So between the Sensor Watch, the LCD Featherwing, and the OpenBook, a lot of your projects are battery powered. How do you manage power consumption to make them last as long as possible before needing to be charged?
Yeah, so this has kind of become a pretty relentless focus of mine. There's two pieces to it, which sort of boil down to like the phases of like standby mode and deep sleep mode. So pretty much all the microcontrollers you're going to work with in CircuitPython or Arduino or anything, they've got two modes. They've got an idle mode where the CPU is running, and then they've got a standby mode where the CPU isn't running. So the more time you can spend in that standby mode, the better off you are. So like with the LCD Wing, for example, I have a clock demo in Arduino, and it blinks the colon twice a second. So just like, blink, 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 like a ticking clock. So you could do that by blinking the colon and then calling the delay function with a 500 milliseconds, and then you toggle the colon again, So that would work. But if you call delay, then your CPU is running because it's using the system tick to determine that amount of time. But if you use Adafruit's Sleepy Dog library to sleep for 500 milliseconds, then the CPU can actually go to sleep, or into standby rather. So that's like 99.9 something % of your second that is just not even awake. It only needs to be awake for that fraction of a second that it's bursting some data out over the I2C bus. So that's kind of one part of it, just trying to stay in standby mode as much as you can. In the case of the LCD Featherwing, I also did a kind of a cool trick with the LCD signal routing where you only have to send one byte over the bus to blink the colon or the indicators. And that's another kind of fun trick. The less data you have to send out over I2C or SPI bus, like the less time your CPU is awake, number one. And number two, especially with I2C, there's fewer zeros on the I2C bus, which means less current kind of flowing through those pull-up resistors. So that's kind of in the weeds, but that's another one where it's like, yeah, the less you can do, the better. So the other thing, and this is still kind of in the standby, well, I guess this applies to both. The other thing is just being really careful about what other gadgets in your gadget are getting powered when you're in sleep mode. So with some early OpenBook prototypes, this is the one where I kind of threw the kitchen sink at the early OpenBook prototypes. It had a NeoPixel, it had a flash chip, it had a microphone preamplifier to do voice commands out of a headset. It was over the top. But I was looking at it and I was like, why is it consuming so much power? It's not supposed to, like, my processor's not supposed to consume this much. And then I realized every gadget that I'd hung on the Christmas tree was drawing power. My mic preamp was drawing power. My NeoPixel was drawing power. So kind of everything in your gadget, like if you tie it to, VCC or 3 volts or whatever, it's going to be drawing its quiescent current all the time. So now on the new kind of OpenBook boards, I gate all the power to those peripherals behind a MOSFET power switch. So let's say that you wanted to make a pigeon camera, put next to a bird's nest or something, like take photos of this is actually a project I built at one point. It took photos of the pigeons on a time lapse. At first, I just powered up one of these little serial cameras and the battery died within a few hours a few days because it was powered all the time. Whereas if you only turn on that camera when you are ready to take a picture and then you turn it off afterwards, then you're going to get a lot more life out of that battery. So that's one thing. The other interesting one, so one of the early OpenBook prototypes, I gated all my power behind that MOSFET power switch, but even when I turned off power to all those peripherals, it was still drawing more current than I was expecting it to. So I'm like, what is going on here? And what I realized was some of the signal lines that actually went out to the ePaper driver and stuff were being held high even though I was going into this deep sleep mode. So it was back-powering some of these things that, even though their power was turned off, the signal lines from my microcontroller were back-powering the gadget. So that was causing them to draw more power than I wanted them to. So I had to drive those signal lines low before I went into deep sleep to make sure there was no current whatsoever flowing to them. And that was another way to get a little more battery life, because you just have to be really careful and make sure that everything that can draw current is configured so that it can't draw current when you're in that kind of mode where you want to be, asleep or drawing less current. So that's half the equation, standby stuff. The other big side of the thing is deep sleep mode. And this is especially interesting to CircuitPython folks because, well, first of all, not all chips have this, but especially like the ESP32 series and the Feather M4 series, they've got a few pins that can do pin alarms, and they've got a real-time clock that lets them do alarms. So with a pin alarm or an alarm, you can put your CircuitPython script into deep sleep mode, and then it goes into this like really, really low current consumption mode where it's on the order of like single digit to low double digit microamperes, and it can stay there it can stay there indefinitely until a pin gets pressed, or it can stay there for, seconds, minutes, hours until you're ready to wake up. And it does restart from the beginning of your script, but in a lot of cases that's fine because, like, let's say hypothetically you wanted to do that clock example from earlier, but let's get rid of the blinking colon. Let's just update the time once a minute. So you could update the display and then enter deep sleep mode for 60 seconds. And then at the end of 60 seconds, your script starts over again. It updates the display with the value of the real-time clock, which is, the current time. And then at the end of that, just go back into deep sleep. So now you're spending 99.9% of a minute in deep sleep mode. And that's where you can get into real low power savings. So actually I did this kind of as a stress test. It was a weather station type gadget I made using the ESP32S2 and the LCD Featherwing. And one of those little 400 milliampere hour batteries that fits between the feather headers. So really small. We're talking 1 or 2 cubic inches. So small gadget. And the setup was it would it would wake up, it would turn on the temperature sensor, it would take a reading, it would turn it off. Then it would turn the Wi-Fi on, upload that data to Adafruit IO, and then it'd go back into deep sleep for 15 minutes. So it only had to be awake for maybe 10, 15 seconds every 15 minutes. So you're up for a minute, an hour. That setup lasted 2 full weeks on that little 400 milliampere hour battery before I needed to recharge it. And if I wanted to make a more robust weather station that I could leave out for a month, double the battery, 800 milliampere hours, and you get a month of battery life. So yeah, deep sleep ends up being a really powerful tool for making CircuitPython scripts low power, to the point where you could actually write a CircuitPython gadget, deploy it out in the world on a solar panel and a battery, and expect it to last for quite a while just on deep sleep.
That's really impressive. Last question that I ask each guest. You're about to start a new project. Which microcontroller do you reach for?
So I gotta say, it's not the new hotness. It's kind of an oldie but goodie. The Feather M0 Basic. First of all, I'm all in on the Feather ecosystem just because I make battery-powered things, and the idea of a battery-powered gadget you just plug into USB to recharge, that's huge. That's the framework for making all kinds of cool stuff. And then the SAMD21 it's just kind of like the Swiss Army knife of microcontrollers. It does so many different things, and it does them all well. So I'm probably going to find whatever I'm about to do will fit well with what the SAMD21 needs or has available to me. And then the classic one in particular, because 2 things. One, I mentioned about low power stuff. There's no NeoPixel and no flash chips, so there's very little in the way of extras, so not a lot can draw extra power for me. But also the little prototyping area, it's really useful to make the gadget into whatever you need it to be. So I'm building a solar-powered gadget for a friend who is doing an art installation, and that little prototyping area becomes a direction pad for navigating a series of menus. Or there's a Feather M0 running my LCD Featherwing testing setup, and that prototyping area gets a power switch just to turn it on and off, so I can leave it off most of the time. If you want to make a atmospheric sensor, solder in one of those little temperature humidity sensors in the little prototyping area. You don't need to dedicate a whole protoboard wing. You can just turn the Feather M0 into whatever gadget you need it to be. I think that's a huge usability win. So yeah, if you tell me nothing other than I'm reaching for a board to do a new project, it's probably going to be the Feather M0 Basic.
And if people want to learn more about your products, where should they go?
So at this point, I'm still on Twitter. We'll see how that goes in the coming weeks. Otherwise, I've got a account on Mastodon, which is linked in my Twitter handle. And oddlyspecificobjects.com is the website where you can check out the things I've made, and there's actually a link to shop.oddlyspecificobjects.com to buy some of the stuff, or you can buy the Featherwing on Adafruit. So
that's great. Joey, thanks so much for being on the show.
Thanks for having me. Really great conversation, and I appreciate it.
Thanks to Joey for being on the show, and thank you to PCBWay for their sponsorship of the CircuitPython show. For show notes, transcripts, and to support the show, visit CircuitPythonshow.com. Until next episode, stay positive.